Hello, everyone. In this talk, I will walk through different parcellation approaches using resin-safe functional MRI. I will briefly introduce the gradient techniques, but I won't really go deep into details because the other speaker, Yetian, will explain more on the gradient stuff. I will also outline a systematic approach for assessing the parcellation quality. So the brain is active even at rest. This video is from Daniel Margulies. It shows that the functional MRI signal when the subject is lying at rest in the scanner. As you can see, these large spontaneous activity fluctuations appear throughout the brain. These intrinsic fluctuations are relevant here because, as demonstrated by Biswa, the fluctuations can be used to measure the functional connectivity in the human brain. So for example, if we put a seed in the posterior cingulate cortex, the time course of the PCC is shown as the blue line. If we compare the time course of PCC and the time course of region A at angular gyres, shown in red, we can see that the time courses are highly correlated, fluctuating up and down together, and the Pearson correlation is around like 0.9. On the other hand, if we place a seed region at region B and compare the time course of PCC with the time course of region B, shown in brown, we see that they are not correlated, despite region B being spatially close to PCC. So in this case, the Pearson correlation is around 0.1. We call this correlation between functional MRI time courses resting state functional connectivity. And this approach of taking a seed region and correlating its time course across the brain is called seed-based functional connectivity. Now, if we move the seed region around the brain, we see that the correlation pattern changes a lot, suggesting that adjacent brain regions can have very different connectivity patterns. And this has motivated many studies to extract the brain networks or parcellations using functional connectivity. So in this educational course, I will first describe several approaches for estimating large-scale brain networks using functional connectivity. Then I will talk about approaches for generating area-level parcellations. Next, I will introduce individual-specific parcellation. After that, I will briefly discuss the gradient techniques. But as I mentioned before, I will really go deep into the details. And finally, I will describe methods to assess the parcellation quality. So now let's start with the network level parcellation. Resting-safe functional connectivity is a promising tool for identifying large-scale brain networks. So brain regions can be grouped into around 10 to 20 brain networks, each associated with various cognitive functions. And brain regions within each network share similar time courses or connectivity patterns. Here, I'm showing you a few examples of network level parcellations estimated by different approaches. These network level parcellation approaches can be grouped into two categories. The first category is hard parcellation. For hard network level parcellation approaches, each vertex can be assigned to only one network. So mixture model is one common approach for estimating large-scale brain networks. So here I'm showing you the 7-network hard parcellation from the year 2011. Different colors indicates different networks. We can see that the networks are not overlapping with each other since each vertex is only assigned to one single network. Mixture model approaches try to group brain regions with similar functional connectivity patterns together. So in this example, even though the posterior cingulate and the medial prefrontal cortex are far away, they're grouped together into one network because they have similar connectivity patterns. On the other hand, even though this region is close to the posterior cingulate cortex, their connectivity patterns are very different. Therefore, this region is assigned to a different network. Another approach for estimating hard network level parcellations is using graph theory. So in graph theory-based approaches, functional connectivity is constructed as a graph. So each graph node here indicates a distinct brain region. The edge between two nodes indicates the connectivity strength between the two brain regions. Here, secret edges represent stronger connectivity. So after constructing the graph, we can apply community detection approaches such as InfoMap or spectral clustering to group the graph nodes into different networks. Another category of network level parcellation is soft parcellation. So here, each vertex can belong to multiple networks. Spatial ICA is one of the most popular soft parcellation approaches. In spatial ICA, the resting state functional MRI data is seen as the decomposition of a set of spatially independent maps and their corresponding time courses. So here is a spatial map corresponding to the default network from Smith 29. And comparing this with the default network generated by a hard network level parcellation approach, we can see that they are very similar. Another approach to create a soft network level parcellation is fuzzy C-means. The idea is similar to the mixture model. So we should try to group the brain regions with similar functional connectivity patterns together. However, the fuzzy C-means allows for weighted assignment of each vertex to multiple networks. So for example, this figure shows the default network, and the yellow color indicates brain regions with a strong probability to be grouped into the default network. And the red color indicates a lower probability for this. Again, if we compare it with the default networks generated by the hard network level parcellation approaches from the Yo 2011 and the Power 2011, we can see they are very similar. So this is good as it suggests that these large-scale networks are consistent across different studies and methodologies. In this table, I list some network level parcellations that are publicly available. You can download the parcellations directly, or you can download the code and apply them on your own data to generate your own network level parcellations. So far, I have described approaches for estimating network level parcellations. Now I will move to the area level parcellation approaches. Here are 3 examples of network level parcellations, including both hard and soft parcellations. However, we know from the systems neuroscience that the cerebral cortex is composed of like roughly 300 to 400 cortical areas, and each area has its own distinct functions, architectonics, connectivity, and topography. Therefore, each of these large-scale networks likely contains multiple cortical areas. Here, I'm showing you another 3 examples of area-level parcellations. So in the next part of my talk, I will describe approaches for estimating area-level parcellations. Similar to network-level parcellations, we can also group the area-level parcellations into hard and soft parcellations. Again, for the hard parcellation, each vertex or voxel can only be assigned to one parcel. We can also use clustering techniques, such as the mixture models and the spectral clustering, to generate area-level parcellations. Here, regions with similar time courses or connectivity patterns will be grouped into the same parcel. In the previous slides, I mentioned that 2 spatially far apart regions can share similar connectivity pattern. Therefore, if they are grouped into the same parcel, then the parcel will be spatially distributed. In order to ensure the spatial contiguity, additional constraint will have to be added into the model. In this way, we can obtain an area-level parcellation where each parcel is contiguous. Another approach for area-level parcellation is the gradient-based approach, a method pioneered by the Steve Peterson's group. So this approach detects local changes in connectivity patterns. This is based on the idea that the connectivity patterns can abruptly change from one location to a nearby location. For example, these two nearby regions have similar functional connectivity patterns, while this nearby region have a very different connectivity pattern. By mapping these local changes across the cortex, we get the following gradient map. Red indicates rapid changes in functional connectivity at that location, and dark color indicates slow change in functional connectivity at that location. Then using some post-processing, such as the watershed algorithm, we can convert the gradient map into the Gordon 2016 parcellation shown here. So these are the hard area-level parcellation approaches. And now let's look at soft parcellation approaches, where each vertex can be assigned into multiple parcels. The most common way to achieve this is by performing the spatial ICA with a higher dimensionality. So here are 4 distinct spatial maps corresponding to the default network when performing spatial ICA with 300 dimensions. This table shows several area-level parcellation approaches that are publicly available. I will now talk about individual specific parcellation approaches. In previous slides, I have shown several approaches for estimating network-level parcellations, as well as approaches for estimating area-level parcellations. So these parcellations are obtained by averaging or concatenating data across many individuals. However, as you can see on this slide, the group level parcellations do not capture individual specific parcellation features. Here are individual specific network level parcellations of 3 representative subjects. Each column corresponds to 1 subject, and the first row is day 1, the second row is day 2. The parcellations are estimated with functional MRI data from day 1 and day 2 separately. So we can see that there are fine-grained network features that are highly replicable across sessions. Area-level parcellations also show highly replicable features across sessions. So this figure shows individual specific area-level parcellations of 3 subjects from Lee 2019. Each row corresponds to 1 subject. The first column is test sessions, and the second column is the retest sessions, estimated independently. But are these individual specific features real? So people believe they are real because these features have been shown to relate to behavior. Since the topography of networks vary across individuals, this can be used to predict behavior. So here is the result of behavior prediction of certain cognitive measures using network topography. The red line shows the accuracy of the HCP megacontrol, which uses the functional connectivity strengths for behavior prediction. Therefore, using network topography for prediction is not worse than using functional connectivity strengths. One recent work have also shown that functional topography of association networks can predict individual differences in executive function. So this figure from 2020 shows parcellations of 4 representative subjects. And here is the result of behavior prediction of executive function measures using association network topography. So the prediction accuracy is around 0.46. Individual network topography also related to heritability. In this plot, the y-axis is the heritability, the x-axis is different networks. This work is from Kevin Anderson. He shows that individual network size is heritable across all networks. And the unimodal networks have relatively higher heritability than heteromodal association networks. Furthermore, the individual network topography is also heritable across all networks. The monozygotic twins show higher similarity in network topography than the dizygotic twins, sibling, and unrelated participants. So far, we have seen that the network topography can be used for behavior prediction. On the other hand, a vast body of literature has shown that the functional connectivity strength can also predict behavior. Using functional connectivity strengths derived from the group level parcellation, the fluid intelligence can be predicted with an accuracy of around 0.2. However, this prediction accuracy can be further improved if we use the individual specific area level parcellation to compute the functional connectivity for behavior prediction. So this suggests that these individual specific features are behaviorally meaningful. Here are some publicly available individual specific parcellation approaches. So far, we have discussed parcellation approaches. I will then briefly introduce the gradient approach. We can extract discrete or continuous representations of brain using functional connectivity. The gradient techniques look for like a continuous representation of brain. So basically, the gradient approach applies nonlinear dimension reduction approach, such as diffusion embedding, to decompose the functional connectivity into multiple principal gradients. In this figure, the purple matrix represents the n by n functional connectivity matrix, where n is the number of vertices. So if we self-correlate this functional connectivity matrix, we will get the blue similarity matrix. So after applying diffusion embedding, we can obtain k principal gradients. So here I'm showing you the top 5 gradients at the individual level. So recent work from Hong 2020 shows that the gradients can also be used to predict behavior phenotypes using CCA. So x-axis is 68 phenotypes, and the y-axis shows 100 gradients. The color represents the Spearman correlation prediction accuracy, and there are like around 18 behaviors can be significantly predicted by gradients. Here are some publicly available gradient toolbox. We have discussed group level, individual level, parcellation approaches, and also gradients. And in the last part of my talk, I will describe methods to assess parcellation quality. We have seen that individual specific topography and functional connectivity can be used for behavior prediction. We can assume that a higher parcellation quality will enable better prediction accuracy. Therefore, behavior prediction can be used as an indicator of parcellation quality. Recall that the cortical areas have traditionally been defined based on function, architectonics, connectivity, and topography. We can also use these criteria to assess parcellation quality. To evaluate function, we can use the task functional MRI data. Here, I'm showing you the task contrast maps and the corresponding resting state network boundaries of 2 MSC subjects, together with a group average map. Blue indicates strong activation in response to hand movements, which corresponds nicely to the orange smart motor boundary. The yellow indicates strong activation in response to tongue movements, which corresponds well to the blue smart motor boundary. It can be seen that the shape and size of the task activation patterns varies across subjects, while also conforming to the resting state networks. Therefore, we expect the activation strength to be uniform within each parcel or network. But how do we measure this? One metric is called the fraction overlap. To compute this metric, we first threshold the task activation map. Then we compute the fraction of the task activated vertices that fall within parcels as opposite to the boundaries between parcels. Therefore, higher fraction overlap indicates better parcellation quality. However, this metric is very sensitive to the threshold level, requiring the user to compute this metric with different thresholds. To avoid the thresholding, another metric is called task inhomogeneity. The task inhomogeneity measure is defined as a standard deviation of task activation within each parcel. Low inhomogeneity means that the activation within each parcel is more uniform. Therefore, here lower value indicates better parcellation quality. This plot shows the task inhomogeneity of individual specific network level parcellation from the 10 MSc subjects. The red dot represents the task inhomogeneity of individual specific parcellation. The blue dot represents the task inhomogeneity of group level parcellation. The black dot represents other subjects' parcellation. We can see that the individual specific parcellation achieves the lowest task inhomogeneity. To evaluate architectonics, we can look at the histological alignment. Here we can see that both the Gordon and the Schaefer parcellations have a good alignment with early sensory and late modal areas. We can align the parcellation boundaries with the architectonic boundaries to assess the parcellation quality. The architectonic alignment can be defined as the mean house of distance between the architectonic and the parcellation boundaries. Lower distance means that the parcellation boundaries aligns better with the architectonic boundaries, so lower the better. In this plot on the right, we can see that the Schaefer parcellation achieves better architectonic alignment. To evaluate connectivity, we can use the resting state function MRI. As voxel level analysis is too computationally expensive, area-level parcellations are normally used to define the region of interest for dimensionality reduction. So we expect the resting state function MRI time courses within a parcel or network to be highly similar. We can use homogeneity as a metric. One way to compute homogeneity is to perform the PCA analysis for each parcel's functional connectivity patterns. The homogeneity metric is then defined as the percent of total variance across all vertices connectivity patterns that can be explained by the first principal component. A higher homogeneity value indicates that the connectivity patterns of vertices within the parcel can be better described by a single connectivity pattern. In this plot, the red dot represents the homogeneity of Gordon's parcellation. And the black dots represent the homogeneity of a null model, where Gordon and colleagues randomly rotate the parcellation 1,000 times. In this way, each parcel is randomly relocated while maintaining the relative positions of parcels to each other. So this is also known as a spin test. We can see that the homogeneity of a Gordon parcellation is significantly higher than the null model. Another way to define the homogeneity is to compute the correlations between the time series within each parcel. Higher homogeneity means that the vertices within the same parcel have more similar time series. So the higher the homogeneity, the better the parcellation. Here is the homogeneity of Schaefer and Glasser parcellations. To evaluate topography, we can look at the regions with internal topography. For example, with the functional MRI, we can map many visual areas using isotopic mapping. Here we can see that the Glasser parcellation has very good alignment with isotopic areas. Therefore, we can align the parcellation boundaries with the isotopic boundaries to assess the parcellation quality. Similar to the architectonic alignment, isotopic alignment can be defined as the mean house of distance between the isotopic and the parcellation boundaries. So lower distance means that the parcellation boundaries align better with the isotopic boundaries. So here, lower is better. The bar chart shows the superior isotopic alignment of the Glasser parcellations. Today, I have discussed several approaches for the network level parcellation that review similar large-scale network structures. I have described approaches for estimating area-level parcellations The area-level parcellations can be utilized as region of interest for dimension reduction. I have also shown the value of estimating individual specific parcellation, as group-level parcellations often obscure individual specific features that are behaviorally meaningful. Similar to parcellation approaches, gradients can also be used for behavior prediction. Finally, I described the FACT criteria that can be used to quantify the parcellation quality. I'd like to thank our group members and collaborators and our funding support. I would also like to bring attention to the repository for women in neuroscience, which is a great initiative to improve the women's representation in neuroscience. So the website above is my WinRepo directory. Feel free to provide any feedback on my talk. So that's all. Thank you.